Okay, welcome to my talk. Just a short introduction. This is more an academic talk. I'm a PhD student in Hagen, and I focus on covert channels and side channels in computer networks since about 2008. I also wrote my diploma and my master's thesis on this topic, and I'm a researcher in Augsburg, and I wrote several books in the context of Linux, and one also, as mentioned, about covert channels. I have two predictions for this talk. The first one is that future malware will be much more stealthy and adaptive than it is nowadays. You will learn what I mean with more stealthy and adaptive. And the second prediction is that we will find new ways to exfiltrate data. I split this talk in three sections. First, I give you some background information about covert channels, the detection, prevention, limitation of covert channels, and afterwards I will go into detail for novel approaches in the area of network covert channels. Because what we have now in the research area will come into practice within the next years, and it is much more advanced than the old covert channels were. So what do we need to create malware or a safe communication for journalists in observed networks? We need a very, very stealthy communication, and therefore our communication should rise as few attention as possible. If our communication rises attention, maybe a journalist is detected and maybe gets into jail, or our malware is detected and maybe the malware will be blocked afterwards. So this is our main requirement. But what did we already have in the area of covert channels? I read hundreds of papers about it, and basically we have three different techniques for establishing network covert channels. The first one is to use packet timings. So we modified inter-packet gaps, sometimes it's also called inter-arrival times, between network packets, and encode the hidden information in the timing deltas between the network packets. This is already an approach from the late 80s, I think 1987, by Gerling or Wolf. And we also can modify the packet order, for instance, the IP ID. Right? We can send normal traffic, IP ID 1, 2, 3, and so on, but we could also start with ID 3, then ID 1, and ID 2 following. And using this manipulated order, we can encode hidden information, only understood by the receiver of the hidden message. Because for covert channels, sender and receiver have to agree on a common encoding of the hidden message in advance. And of course, we can put hidden data in so many fields of IP, of TCP, ICMP, and so on. There are so many approaches available. And we can do this since ages. But even nowadays, new tools come up and do the same. And they show, hey, we can hide in some other new protocol. We can hide data in some flag and so on. But that's actually quite boring, and it's not new, and it causes anomalies, and we can detect it, at least in theory. So what we have, the available tools we have are basically crap. The hiding capabilities are from a research perspective. They cause anomalies, we can detect it. For instance, there is one tool, I forgot the name, that hides data like this. You have two version, the version number in HTTP is used to encode the hidden information. Everybody can detect it. Or ping tunnel uses a magic byte. If you know the magic byte, you can detect ping tunnel. So it's useless. No, it's not useless. You can use it to bypass a firewall that blocks your protocol, and if you can use ICMP to bypass the firewall, it's good. But if you want to keep a low profile, you can forget it. It's useless. So what I will talk about now are very old research techniques or techniques to detect covert channels. I selected especially old techniques to show you that we can do this detection since ages. Camera was the first to introduce an approach. It's called the shared resource matrix. He split it operations in sub-operations with individual operations and tried to figure out whether an attribute can be read and modified. Because for a covert channel you need to modify, i.e. to send traffic, and to read traffic, to recognize the modification. That's the part the covert channel receiver has to do. So in this table you can you can try to find a possible way to communicate using the operations for a covert channel using the shared attributes. Actually, this is not the original shared resource matrix methodology. It's an extended version from McHugh, developed in '95, but based on the original version. Later, in '91, also again camera, but together with Porras, they introduced a means called covert flow trees. Using covert flow trees, source code is checked automatically. Again, a matrix is built that shows you which attribute is referred, modified, or returned by which function. And the good thing is, using this approach, you can even recognize indirect covert channels. The pictures are from the book of Matt Bishop. So you select an attribute, for instance logged, and you have to modify it, you have to recognize the modification, and you build a tree with the possible ways of communication using the functions. This is just to give you an overview. Actually, the approach is a little bit more complicated, but I just want to give you an idea. Later, several other approaches came up, like the pump, one-way links, blind write-up, store and forward protocol, and such things. The basic idea is always the same. We have a low system, i.e. with a low security level, and a high system with a higher security level. And the Bell-LaPadula model, you probably know it, forbids some kind of communication where the low system gets information from the high system. So we have to prevent that the high... Can you hear me? Okay, can you hear me? The high system is forbidden to communicate, to write down information to the low system. That's the purpose of all these approaches. And in between, we usually have a buffer that prevents a general technology that prevents the write down of the information. Usually, we only allow acknowledgement messages to be sent down to the low system. And even these acknowledgement messages, because they could build a covert timing channel based on the number of acknowledgement messages per time slice. Even this number of acknowledgement messages is limited by the pump. It's a device developed by the Naval Research Lab. And it prevents, or it doesn't prevent covert channels, but it limits the channel capacity. We also have this since 1983, I think. It's developed by Kang and Moskowitz. And a more recent approach, but actually also from the 90s, late 90s, are traffic normalizers. They were not designed to prevent covert channel communication, but they are very efficient for covert channel prevention. Nobody is aware of the fact, but actually they are very, very useful because they clear, unify, modify redundant header areas, unused areas where we usually place our hidden information into. Yeah? So if we hide data in the reserved flag of the IP header, these normalizers clear it. Most normalizers can do that. I think Snort normalizer, OpenBSD, PF scrubbing, they can do that. There are some problems with it, like the cold start problem. Normalizer bootstraps, notices some existing TCP connections, but does not know anything about the handshake and so on, and we have inconsistent TCP transmissions. What also must be considered a problem because you can see it in the picture. It's from a paper by Handley et al. The attacker sends multiple packets with the same sequence number. The IDS or normalizer is located between the sender and the receiver. Some packets reach the destination, others do not. So the IDS is not aware of the rest of the network topology, and so it cannot determine whether one packet will arrive or not. And so whether the message is root or nice is hard to solve. Covert channel research led to improvement of that idea called the network-aware active warden. That was actually designed by another PhD student and to counter IP version 6 based covert channels. So the new approach is that the normalizer is aware of the network topology and it will be able to understand whether a packet with a given TTL will arrive or not. Also very old, but we just recently applied it. I cannot talk about it because papers in review, but there's an approach by Hu. I forgot the first name, but his name is Hu, H-U, from 1991. They already had virtual machines in the VEX security kernel, and to limit the channel capacity of timing channels between the virtual machines, they introduced fuzzy timings. So the real system has, the host system has knowledge about the real time at which events occur, but the virtual machines are notified with a slightly incorrect time. So the synchronization between the covert channel sender and receiver is not accurate, what limits the covert channel capacity in 1991. And that's amazing. We can use all these old approaches even today. Okay, there are so many other approaches, but due to the limited amount of time, I will not go into detail about the other approaches. For instance, we can use C4.5 based decision trees to detect covert timing channels, to detect protocol channels. We can evaluate BPMN business processes by modifying, by transferring them into some kind of colored Petri net and evaluating different circumstances. Was done by a research group from University of Freiburg, I think. We can introduce spurious processes in a trusted computing base that disturb local covert channels in an operating system. We have statistical approaches, especially for network timing channels. There are many statistical approaches. We have code modifications and so on. I wrote a book about it, and I wrote very, very detailed about all these things. So I think it's even available for download on some shared website. You can download it. As an author, you don't earn much money with the book, nevertheless. But if you cite me, I'm happy. Okay. So in summary, for this first part, we have a lot of techniques to establish covert channels. We have a lot of techniques to hide, to detect, limit, and to prevent covert channels. And most of what we already have is very old, up to 30 years. Actually, covert channels were first introduced in 1973, so it's 40 years. Okay. Now I come to the main part of the talk. This is basically some extract of my PhD thesis, I'm not the only person who working in that area. A few other people do as well. So I will give you a very short introduction about the related work. Just one slide. We have internal control protocols. So we use the hidden area of the covert channel and introduce a protocol like a network protocol header Ray and Mishra did that in 2008. They introduced the 8-bit protocol to realize reliability, transaction-based communication. We have natural selection to evaluate whether protocols are acknowledged or not, and we calculate survival scores for protocols to select the most useful network protocols for hidden communication. We have adaptive covert communication via Roshkin et al. They filter out non-rooted or blocked network protocols. So let's say you have a covert channel using ICMP, you block it, and the channel notices that you blocked ICMP and switches to another protocol. So you change your firewall configuration, but the covert channel changes as well, and then you have to block it and find it again. That is pretty cool, and already done 2008. My research focus was on protocol hopping covert channels. Protocol hopping covert channels switch their protocol transparently for the user. You do not notice it. I did that already in 2007. So you have many network protocols, and some of them will arrive. So even if you block a subset of it, there's still a remaining set you can use for the communication. They have an internal sequence number, so if some packets got lost or got blocked, your message will be received nevertheless. There's also a concept called protocol channels. Because I need both terms later, I will just explain both approaches. In a protocol channel, you assign a bit value to a protocol. So if you want to transfer the message 1011, and once 1 is transferred via the occurrence of an ICMP packet and 0 is based on UDP, then you send ICMP, UDP, ICMP, ICMP. It's a very basic idea, but hard to block. And the protocol channel, on the other hand, is independent from the used protocol. So you can use every protocol, but you hide payload in it. And you put a control protocol in the covert channel that takes care about the reliability and so on. You can also use, for instance, error correcting or error detecting codes here for the protocol channel. But I just want to give you an overview. So what we can do now is that we can build covert channel overlay networks with different access points, and we can access the overlay network using different protocols we use to hide the data in, right? And so we advance covert channels. We can, as mentioned, switch the protocol. We have adaptive communication, and we have a so-called network environment learning phase. In the NEL, peers determine the possible communication options between each other, because a priori they do not know which protocols they can use. Or maybe they use different covert channel software versions and something like that. So what I introduced is control protocols with version numbers, with different protocol sets, and that allows me, I go back one step. For instance, let's say I upgrade this part of the covert channel overlay with a new version, and he accesses with a different version. But these two systems can agree on one supported version of protocols they can use, even if some protocols are blocked. But that's based on the work of Roshkin et al., because they did that already earlier. I just improved it because there's actually a two-army problem within the NEL phase. And the really cool stuff is that we can make these internal control protocols very space efficient, because if it's space efficient, we need to transfer less data, what rises less attention. Each bit we have to transfer can lead to the detection of our covert channel, and that's our goal. We do not want anybody to detect us. And also we can build very dynamic headers. I will show you later. But first, I need to introduce the terminology we developed. It's very, very simple. The underlying protocol, I think, is very easy to understand. It's just a protocol we utilize for the covert channel. If we hide data in IP version 4, then the underlying protocol is IP version 4. in this area, in the protocol, we define a so-called Covert protocol area. I choose this term because it's conformed to information hiding terminology, to the existing terminology. For instance, we use the TTL, 2 bits of the TTL, and the DF flag in IP. And these 3 bits together form the Covert protocol. And in the Covert protocol, we put the micro protocol. That's the Covert channel internal control protocol. It's called micro protocol because it's tiny. We only have a very limited space. This is why we need very space efficient protocols, because this space is not just for the micro protocol, it's also for the payload. If you have only 3 bits, you don't have much space for a protocol, and if you also want to transfer payload, you have a problem. So you need to develop very tiny protocols. One layer is usually, in that case, not enough to provide enough space, so we combine multiple layers to one bigger Covert protocol. Of course, depends on whether you need routing or not, so you cannot probably not always use Ethernet. This is really, I really like that slide because I wanted an approach to ensure that the micro protocol rises as few attention as possible. And I was looking for a technique to ensure that the micro protocol is conformed to the utilized protocol. So we do not want to violate the rules of the underlying protocol. The micro protocol behavior within the utilized protocol must be exactly the same. It should, you should not be able to distinguish above protocols. So it took me long to get a good idea. I played around with Petri nets and lots of other means. At the end, the formal grammar was the solution. I found it in proceedings also from the 70s. They were not digitalized, and I had to order them via real mail, not electronic. I had to wait 2 weeks. And there was an approach by, I think, Horang Gozo from 1977, and he modeled protocols using regular and context-free grammar and did a language inclusion test to test whether the protocols are conform. And I applied that approach. So it's divided in 2 layers and 6 steps. In the first layer, we have the underlying protocol. So we define the Covert protocol in the underlying protocol and evaluate the occurrence rate of the bits of the underlying protocol. And then we define the micro protocol and evaluate or estimate the occurrence rates of the bits within the micro protocol and map both lists. What we achieve is that it is nearly equally likely for a micro protocol bit to occur than a bit within the underlying protocol. So it's hard to distinguish. Afterwards, both protocols are modeled using formal grammar, and we model the whole behavior, even connection dependence, even errors in implementations. There's a paper at the IEEE Security and Privacy in a few months. It will be presented. They did the same, but they present it now. We presented it already in September, but for protocol-specific covert channels. They did it a little bit more general for network steganography, but we got no citation. That I really don't like that. But by ensuring that our microprotocol the grammar produces a language subset of the Covert protocol, if this condition is given, we do not violate the rules of the Covert protocol. So we rise, again, only very, very few attention while our microprotocol is operating. And that, I think that's really cool. Okay. And again, the next task was to shrink the size of the microprotocols. So I again thought, what can I apply? And I always first look on the very old stuff. And I found compressed slip. That's you know slip. It's older than PPP, very old, and C-slip is from I think from 1990. And I just combined the idea of IP version 6 and C-slip to status updates. Status updates modify a connection based on an update of a status. For instance, if I want to change the destination address of my covert channel connection, I send a status update. But I only transfer it once to configure it or to change it. I don't transfer the source or destination address again, so I save a lot of space. I mean, in a covert channel overlay, you usually do not use IP addresses with 32 bits. You don't have so much space, so you have your own addresses. And all peers share a table of status updates. A status update is a combination of the update type and its value. For instance, here's the type, 0, 1, and the meaning is the destination address update, and both values follow. So first you indicate how to interpret the value, and then follows the value. Like that. Here's a covert channel proxy, here's a receiver, and I want the proxy to forward some payload, ABC, to the receiver, and therefore I set the destination address using a status update, and that's it. And afterwards, the proxy forwards all the information. I can send thousands of payload packets here without, again, specifying the destination address. And this approach saves a lot of space. I can combine them to sequences in one packet if I have enough space. And to show that it's really efficient, we redesigned the already efficient 8-bit microprotocol from Ray and Mishra. I split the header in two subheaders. The first thing is here the TOU bit, type of update bit. I extracted the start and stop flag for the transaction to start and to end the transaction and put it in a separate header. So I only need to transfer 7 bits instead of 8 bits in nearly all cases. And if a transaction comprises at least 6 packets with Huffman coding for TOU, or 7 packets, I think 6 packets without Huffman coding, we are more space efficient. However, it's not perfect because for initial connection setups, we need to transfer a lot of status information. We have overhead because we need to transfer the TOU, the type of update values. So it needs some, it's not efficient for transactions with only a few packets. But we can improve over the existing approaches in all other cases. And the Ray and Mishra protocol was already very, very space efficient. If you apply that to ping tunnel, you are more space efficient from the first packet on. But ping tunnel is very, very space wasting and not optimized. Next interesting thing is I was lucky and I got a master's student who applied the status updates approach to build dynamic routing in the covert channel overlay network. He discovered that covert channel overlay networks are like ad hoc networks because our underlying network topology can change at any time. We cannot control it, and we have to. We want a functioning dynamic routing nevertheless, so we have to find some approach to handle these circumstances. The first, to present dynamic routing, or actually not so dynamic routing, where a research group from Poland, and they used the random walk algorithm to achieve the routing in the covert channel overlay network. Peter Barks, he used optimized link state routing. So we wanted to, here are the requirements, we wanted to reduce the size of the routing messages to raise as few attention as possible. Therefore, status updates were used. We wanted only a few overhead. That was done by using the optimized link state routing. And we can use our own addresses. We do not use IP or something like that. It's too big. The student decided to use optimized link state routing because it's very suitable for mobile ad hoc networks and produces small routing overhead. And this was again reduced by using status updates. And the really cool thing is he came up with a really good idea. You all know quality of service, but he introduced quality of coveredness. So we can optimize the link for the coveredness. And that's really, really cool. I mean, you can theoretically build a real overlay network with covert channels, and you can optimize the covertness. I skipped the math part for the previous topic, but we already can minimize the packet count. We can minimize the overhead of connection between peers, and but I think this is even so much cooler because I even like the term. He built an extendable architecture where you can exchange the covert channel techniques in a transparent way. So you can add lots of new technologies. You can add a new hiding technique for HTTP or a new timing channel or whatever you want. It doesn't matter. I show you later. He implemented my concept of protocol hopping covert channels and the network environment learning phase. And this is also a really good idea of him. I think the initial idea came from the Grey World Net team. They did a lot of covert channel research, and they figured out that you could use tools like the Google Translator to build a covert channel without the need that the Google Translator is aware of the covert channel communication. So for instance, agents are aware of the communication, and drones like the Google Translator aren't. And agent 1 and 2 want to communicate using the drone. If this is the Google Translator, the agent requests an URL from agent 2 using the Google Translator to translate it. The translation, nobody cares about it, but the hidden information is in the HTTP address. So it forwards it, but is not aware of the covert channel and is not part of the covert communication, actually, of the route plotting process. We added some type of updates to inform the peers about the peers and the other peers in the overlay network, about the routing topology, and he only required 4 TOUs for that purpose. So it's very efficient. You only need 2 bits actually if you only implement the routing. And this is the architecture of the tool. You have a command line interface, you have the routing and microprotocol subsystems, and a unified API. This API can control all the technologies you implement here. So if you want to add a new covert channel, only you know. You just add it here. You just write a module for it, and then it's used by the system. But interesting question was to find out what can we do to counter these covert channels. I found a tool called DelayNet that was actually that's a small Perl tool to simulate network data loss in metropolitan area networks, and it uses it uses IPQ to redirect packets in the user space and delay these packets. So I thought, why shouldn't I introduce delays on protocol switches? Because all these covert channels apply protocol switches. And if I introduce a delay, I can probably destroy the hidden message, especially for protocol channels. And it worked well. So here's an example. We want to transfer the message, this message using a protocol channel. And we introduce a large delay of 1 second on a protocol switch. So UDP comes in and is forwarded. Now a protocol switch happens, ICMP packet delayed. Next ICMP packet creates no protocol switch and is directly forwarded, and so on. And the hidden message is corrupted afterwards. So the approach is very easy. We can limit the maximum error-free bandwidth of the covert channel very efficiently using either a constant or a randomized delay. The randomized delay is even more efficient. Yes, in the end, it's an optimization problem between usability and security, like in so many cases, because the administrator has to configure the delay. However, there's one problem, and that is protocol hopping covert channels with sequence numbers, because they can resort the hidden message. Okay. Danke. If you have an internal sequence number, the receiver can resort the packet sequence and can recalculate the original payload. So if we destroy the original packet sequence, it doesn't matter if you have an internal, if you have a microprotocol with a sequence number. Okay, the summary is we can do the protocol hopping, we can do overlay routing, it's dynamic, we have agents and drones, we have upgradable covert infrastructure, we can access the overlay network in a mobile manner, we can optimize the microprotocols to raise as few attention as possible using formal grammar, we can minimize the size using status updates, we can utilize multiple layers for the covert protocols, and there is one active warden, but that cannot counter really good microprotocols. So at the moment, we can do nothing against these techniques. There's just no approach available, because each technique you block, you can just implement a new one, or you can use them. You can use one of the set of protocols or covert channel techniques we currently cannot block, because there are hundreds of techniques for covert channels. If you consult the literature of the last 20 years, you find so many. I mean, for nearly every network protocol, you have some hiding techniques. And it's so easy to spot new hiding techniques in other protocols. It's just not complicated. If you understand it once, you can do it again for every new protocol. Okay. Last part of the talk is about data leakage and covert channels in the building automation area. Because I thought, how can we exfiltrate data in future? Let's say new systems come up to block our hidden communications in the usual TCP/IP networks. Why not use the building automation network to exfiltrate data? And an interesting aspect was also to observe data, because if you use side channels are defined as covert channels without intentional senders. So they leak, but there's no intention that they leak data. If we have side channels in the building automation area, we can observe everything in the building. And for instance, if I'm an employee and I want to steal a document from the manager's office, I can check side channels in the BAS and observe whether my boss is currently in his office. If he's not, because light is turned off, temperature is low, no presence sensor detected a person present in the room, so I can go and steal. Or I'm a burglar. I go into the basement because there's no light turned on and everybody is in the second floor or something like that. This is getting really interesting if you think about ambient assisted living and e-health. There are already many pilot projects. I know at least one in Austria that exists since 2011, where elders are observed. And because there's an interconnection between the health data, like blood pressure and so on, and the building automation system. Because the building automation system, if you get really ill, really sick, then the doctor is called, and that's done by the building automation system. So if we have a side channel in the building automation system, we even know health data. This is really, really critical in my point of view. For the covert channel, we add the attentional sender and we want to exfiltrate data. So how can we do that? We hide data in network protocols or in the abstract behavior of the building. We can either sniff the exfiltrated data between buildings because they are interconnected usually via simple UDP encapsulation of KNX or BACnet, and it's never encrypted. there's a standard for BACnet, for instance, that allows encryption, but I talk to the companies and they say nobody wants to encrypt it. Even the companies who sell BACnet since ages, they had never one customer who wanted encrypted BACnet, because the persons who do the administration of the buildings, they say cryptography, that makes everything more complicated. I don't want it. Just put it in my house like it always was, and I don't want to care about features. It's complicated. I just want it to run. This is perfect. And or we connect directly to the BAS and sniff the data there, because in BACnet everything is broadcasted, nearly everything, and so it doesn't really matter where we collect the data, and we get all the information we need. So what happens if a covert channel is established in a BAS is that either a write down or a read up is taking place. So my boss's temperature in his room is written down to a low user, me, the employee. I shouldn't know the temperature in his room, and I shouldn't be able to request it, so that it would be a read up. In joint work with a student and a professor in Augsburg, we developed actually a very simple solution. The BFR is the BACnet Firewall router. It's an open source software. And the idea is as follows. We split the BACnet environment into multi-level secure zones. So we, for instance, have an area at the secret level for sales, and confidential level for some research project or something like that. And we configure the security policy on these secondary BFRs. So they are basically just filtering requests and response messages, that would break the security policy of the BLP model. And the primary BFR just does take care about the routing. In that case, it is just an example. The secret device tries to, the top secret device in the top secret network tries to write down information, i.e. to turn on the heating in a secret level, that's here. But the top secret level BFR prevents the write down. So it will not even reach the first level BFR. It will not forward the data. In our scenario, these second level BFRs are always responsible for the filtering. So to conclude that part, we can say there are site and covert channels in building automation systems. They are of a high relevance because of the health data, because of the observations of people and events in buildings. We can prevent covert channels and side channels both with the same approach in BACnet by introducing very simple topological changes using an open source software. But the BFR is unstable, its documentation is more or less not existent, and the configuration is a mess you need to stack. It's a lot of XML you have to write, and you have to create stacks, and really the documentation is bad. So if there is any volunteer in the audience who wants to write a useful software, a good BACnet firewall software, I would really appreciate it. Let me know if you do that, and I will maybe include it in my next talks if it's stable. So, but the BFR is really, really crap, and I think the last release was 2007. But what can we conclude for the whole talk? First thing is, we have many, many techniques for covert channels. Not all of them can be detected. We have so many techniques to detect covert channels. Yes, we can limit them, we can detect them, and we can prevent them, some of them. But even these approaches, I mean, nearly all of the techniques are coming from academia. We can detect covert channels in packet traces, but we cannot, for instance, detect them just in time. We have a lot of means for detecting covert channels in software, in code, but network covert channels are not so easy to detect. as long as they do not hide data in HTTP version 8.9. And these approaches are very valuable for future malicious communication, for botnets, but also for journalists. But journalists are not aware of it, so they don't use it. If journalists would be aware of using these technologies, they would be much more safe, but there is no good software available for them to do that. The paper I mentioned, the S&P paper that will be presented, I think, in June, they analyzed all these tools that do network steganography. They try to let traffic look like Skype traffic and so on. But they found, for all of these tools, they found detection means because they were not not exactly conform to the behavior of the real protocol. For instance, they didn't really implement the original errors in the implementations. And that allows to distinguish real protocol and data hiding protocol. Using the formal grammar approach, on the other hand, that I just showed you, enables exactly that goal. So we should focus on such technologies. We have covert and side channels in building automation systems, but we can prevent them. That's basically easy. But nobody will do that because you do not change the topology in a building. People do not want them. They are not interested in it. So you can, for the next 10 years, probably you can exfiltrate your confidential data using the BAS. Nobody will ever notice. But since this is a professional audience, I usually give talks to the academic audience, or gave talks to the academic audience within the last years. So I thought this is a really good chance to send a message to the professional audience, the people who really do that stuff in practice. And in my opinion, you are the people who can really enable the technology. You can bring it to the journalists. And if you want to become very well known, you could probably already work on the future botnet detection because you now know what the botnets will do in future. And if you find a way to counter the botnets, you will be the star for the botnets in 5 or 10 years because they will find out what we did in research and they will do it. So that's my message. Thank you for your attention. And here are some papers and books and so on we published. So if you want to read them, most of them are online on my website.
Steffen, thank you very much. Are there questions?
Hi, you mentioned that machine learning techniques have become popular in your for your research.
Yeah.
So as I see it, they have also become popular in image processing and audio analysis. Mm-hmm. Could you elaborate more on the application of machine learning techniques? Like, are you trying to fit some sort of Gaussian model to identify delays? Like delays in binary covert channels or something? Or how do you use those machine learning techniques?
I only know 2 machine learning based approaches and they all use C4.5 to detect covert timing channels based on the inter-arrival times of packets. And they take 2 parameters basically. The first one is the time between the packets and the number of packet switches per n packets. And that's enough. We also did such a machine learning approach using C4.5, presented it at last year's LCN. And the paper is that one. We can detect protocol switching covert channels based on the time between the protocol switches, not the time difference between the packets, but the time between protocol switches, and we used the number of protocol switches per 5,000 packets. We only need these 2 values, and if the channel has 4 bits per second using 2 protocols for the protocol channel, we have an accuracy of 98% or so. But we need traffic recordings, and that's not really practically applicable, I think, at the moment. But there is no, I'm not aware of much other machine learning approaches in covert channel detection, but,
Yeah,
I expect some to come up.
I'm just asking because, as it looks to me, you have strong statistical dependence, and machine learning techniques are a very efficient way to model this. So,
yeah, I think some new research will come out in that area. I really expect that.
Okay, more questions? Everyone's waiting for lunch, right? Okay, so Steffen, thank you very much for that interesting talk. Don't take that, remember the German law, there's a paragraph telling you not to break into computer systems, so take that for good purposes. Yeah, just the message before lunch.